So we've got these specialized problems that I'm asking you to factor, and if you miss class, you're going to need to understand that these are what we call the difference of two squares. Alright, it's a subtraction problem, therefore the difference, and two perfect squares because 4p squared is a perfect square. In other words, you can say what times what gives me 4p squared? It's 2p. So 2p times itself, 2p equals 4p squared. 9 is a perfect square because 3 times 3 equals 9. So a perfect square is something that will factor into a term times itself will give you that term. That was probably not a very good textbook answer, but anyway, the difference of two squares always factors. So here's a new rule to avoid our long factoring process with busting the bees, which we're going to talk a little bit about at the end here. So you can factor this into the square root of the first term plus and minus the square root of the second term. So that's that 3 coming from the 9. And the 4p squared, the square root of it was 2p. So 2p plus 3, 2p minus 3. Let's just prove it. 2p plus 3, 2p minus 3 using the box. And I just want to prove to you that that is the correct factoring of that original binomial quadratic up there. 2p times 2p is 4p squared. 3 times 2p is 6p. 2p times negative 3 is negative 6p. And 3 times negative 3 is negative 9. Therefore, the like terms right here in this box, they cancel each other out. So you end up with 4p squared minus 9. Right? And these canceled out. So it kind of proved that this was the correct factoring of that original expression. So if you'll take a look with me at this next one, you could do several of these on your own, but I wanted to highlight this one because some people they forget that 1 is a perfect square because 1 times 1 gives you 1. So this one factors into the square root of the first term. Square root of n squared is n, and then plus or minus the square root of the second term, and you can grab a calculator and do the square root of 1, not negative 1, but 1, and you'll get 1. So that's the correct factoring. I could go through with the box and do it, but you probably don't want me to prove it. Okay, and now I'm going to skip ahead because that was the first 5 problems, so make sure you do the other 3 on there. And I'm just wanting to take you down the traditional, how do you handle this with our factoring method that we've learned called busting the bees. Alright, so first thing I'm going to do is check for a GCF. Is there a greatest common factor? I was very hopeful there was. Common factor between 25 and 40 is 5, but 5 doesn't go into 16. A common factor with 40 and 16 is 8, or 2, or 4, but none of those numbers go into 25. So there's no GCF, so I skip that step. But I always ask up front. Then I'm going to label my A, B, and C values, and I'm going to populate this X that we've learned about. A times C, that's 25 times 16. Turns out that that is 400. All right, and then I put the B, the basement, down here in the bottom of this. And I'm asking with this X, so we're in what we call X Games mode. Stole that from TikTok. But anyway, 400, 2 things that multiply to get 400, but add to 40. And, you know, I'll be honest, I mean, nothing comes to mind right away, but I grab the calculator and you do the table key, and I put in 400 divided by X, and the table key will give me a list of X, Y values from 1 to 400, 2 to 200, and so forth. Now I'm not going to go through the whole list, but eventually it comes out to 20 and 20, and I noticed that, oh yeah, 20 times 20 does equal 400, and 20 plus 20 equals 40. Okay, so what do I use that for? I take that is going to tell me how to split up the middle term or the B term. So I'm going to rewrite this expression in this case to 25n squared plus 20n, so I'm using what we came up with in this X to figure out how to split up the B, or bust the bees as some people call it. So this method is referred to as busting the bees. plus another 20n, and that's only because it showed up twice here in the x. And then finally plus 16, and that came from the c value. So we rewrote the original algebraic quadratic trinomial as a polynomial, 4-term polynomial, but it's still a quadratic, and it still is equivalent. You might be tempted to say, oh, hey, 20n plus 20n is 40n. That's true, but we broke it apart for a reason, and let's find out what that reason is. We're going to, so I split it up for a reason, and that reason is because I'm going to group the first two terms and the second two terms, and then I'm going to pull out GCF. So I'm looking in this, and I find out that n is a common variable in there, and 5 is a common number, all right? And when I factor that out, I say 5n times what gives me 25n squared? That's 5n. 5n times what gives me 20n? That's 4, all right? And then I go to the next thing, I plus, and it looks like a common factor is 4. And what's left? Well, 4 times what gives me 20n? That's 5n. 4 times what gives me 16? That's 4. And it's no coincidence that these two are alike. That goes in one of the binomials that is my solution to this. In the other binomial, I pull out the common factors that I pulled out of those two expressions, and that goes in the other one. So this is 5n plus 4. Whoops. And times 5n plus 4. Could have also been written as 5n plus 4 squared. Those two answers are the same, okay? And if you multiply those back using box or FOIL, you would see that it actually does come out to this original expression. All right, you give it a try. I think I have some other ones here. Ooh, I'll just give you a hint on number 13 because it's unlucky. There's a GCF in here, and man, I wanted to say it was negative 12, but negative 12 doesn't go into 66. It looks like it's negative 6. Factor out that GCF of negative 6 first, and then you'll have 2x squared minus, no, plus 11, because I factored out the negative 6, x, and then minus 6, because negative 6 times negative 6 gives positive 36. Now that I've got that GCF out, continue with your A, B, C process, figure out how to bust the B's, and do your group factoring thing. Eventually you're going to come out with a set of binomials, and don't forget that that GCF that you pulled out is part of your solution, so it's going to be negative 6 times however that whole process with the x thing factored out for you. So that's get you started.